both the quiz,
and the remaining tests.
oh, sorry, the remaining test and the midterm evaluation. So a lot of you like us to collect homework every lecture with and without a quiz. So we'll do that. So moving forward, we're gonna have a quiz today. But despite that, please upload your homework. So homework will be collected disregarding quizzes or no quizzes every lecture. So make sure you do that. Is that clear? So there was a comment that everyone wants to, not everyone, I mean, a few of you want to see that done. Some of you asked for answer to the homework. Do you know where you can find them? It's meant to be a joke, but it's not very funny. First of all, you know the solution available online to all the problems, right? I mean, I don't need to tell you where to look. Aside from that, in the appendix, which I asked you to look at the first day of the lecture, all the even homework problem, the numerical answer is given. All right. So what I'll ask Mike to do moving forward is we will, on the day that the homework is assigned, we will post the answer, the numerical answer, to the odd homework problem. Does that make sense, Mike? So that you can check it. Yes?
I checked my textbook and it doesn't have like the answers at the end.
Oh, I'm sorry. My mistake. That was the older edition then. I assumed they have done the new edition. So on the new edition, the 8th edition is not given. It's not given. Okay, then Mike, can you post both? But just a numerical answer, not the whole solution. Just the numerical answer for you to check. But having said that, I don't want you to exceed the estimated time that I told you required to do the homework. You get other commitment, you know, it's not productive and beneficial for you to spend twice the amount of time that I think you need to do the homework. Is that clear? And for many reasons, I'm not going to change the homework grade. It's 3%. I'm repeating myself in the first lecture that the solution is available online. I don't want to encourage you to copy and be dishonest. So there's no change in the way you will be graded for the final exam. That's a contract we agree on the first day, and it's not going to change. And the exact distribution is posted online and at tablets. You can look at that. Final is 40%, the two tests is 40%, quizzes is 12, and the homework, sorry, I did it wrong. The final is 4, this is all online, all right, and I'm just repeating it. Final is 40%, the two tests is 45, homework is 3, and the quizzes is 12. And that's not gonna change, that's what we agree on from day one. Suggestion about more numerical example, we'll try to do that. I think that's always a desire from you. So the fire hose problem is one, and we have yet another one that uses the Moody diagram. So as much as possible, we'll try to use numerical examples. Extra homework and practice problem, we'll definitely do that prior to test 2, give you a whole set, and maybe have a few more that you can work on for your own benefit. Okay? I think by and large, that's all the feedback I want to share with you. So I'm going to pass out to you the quiz for today. Face down, please don't look at it until I tell you to. At the end of the lecture, it may take a little while, so I would like to give you like 10 minutes to have that, have sufficient time to do it. So let me open the floor for homework due today. Any question you have on especially problem 8.14, deciding which direction the flow will go, up or down, is not obvious. Anyone who wants me to look at any of the homework, I won't go over them unless you ask. And that was some of the suggestions in the feedback. Yes?
How do you know that the head loss specifically determines the direction?
I'm sorry, I can't hear you.
So I was doing it, and what I found was like the head loss being either positive or negative to determine the direction would make sense. But when you have something where it's kind of like slanted, how do you know exactly like which way that's going?
Okay. So let me take a moment to first set up the problem very briefly, and then I will revisit what we covered last time. by way of the energy equation. Question is which way the flow will go with a different in pressure and also a change in elevation, right? But before we can answer that, let's revisit what we did last time. Because this will be the last key equation you need in fluid, and you have seen that in a very different form in thermal for the concept. And the physics is the same. So here's one example, which we'll work out in detail. That homework is another example of how energy equation is needed to understand the physics of the problem. For the homework is simply knowing which direction the flow will go. For this in-class example, is trying to determine how fast is the velocity exiting my nozzle. So here's what we did last time, just to recap. And that will be what we spend the whole lecture on today. So the left look almost like the Bernoulli, but it's not. So I want to decouple Bernoulli with energy equation. All those terms are somewhat familiar to most of you, right? You've seen it in a different format, like P plus half rho V squared of rho GC. That's one form. And this is similar in that it has taken the entire Bernoulli equation and divided by rho G. But the resemblance stops right here. Beyond that, this is from the energy equation, of which this H sub F is very, very important and is the pinnacle, and they answer the question that was just asked. Someone remind me, what is this called? What is the unit of this entire equation? Length. Meter. We call it head. Head. So the last term is called head loss. And here's the catch. It's the loss in thermodynamics. You learn about irreversibility. Ring a bell? Entropy generation. Can entropy be decreased in a cycle? What is the second law tells you? Entropy in the universe will always do what? Increase. Losses due to friction is an irreversible process. The friction slows down the flow, energy is needed to recover it. Once that's done, you can't get it back. It's gone. It's gone. As such, and we'll go into detail in 2 lectures, as such, this X sub F, frictional head loss, must be what? Must be positive. Cannot be negative. If you do that, you violate the second law of thermodynamics. Losses due to friction always cost you money and you cannot recover it. It's gone. It's gone. It's lost in the universe. You cannot get it back. That is the key in answering this homework problem. H sub F must be positive. So when you do that, with that in mind, if you now do this homework, so the solution will be posted today. So I'm just going to pick an assumption. And I'll tell you why later on. I just assume the flow will go uphill so that I have point 1 in here, or rather point A, and point B in here. Assuming the flow will go uphill, and that's now what I call my flow system. System not the same context as a piston and a cylinder. System meaning a pipe, then we have pump, valve, etc., etc. All right? So I have a very simple problem, a constant diameter pipe. Now I'm assuming the flow will go uphill with the pressure given, with the change in elevation. I can now apply my energy equation from point A as my initial point. I have simply take the term 2 on the left-hand side, move it to the right-hand side. Can you see the relation between this equation and the one on the left? A been changed to 1, or rather 1 been changed to A, B has been changed to 2 has been changed to B, but it's the same equation, right? So you were told this straight diameter pipe had no pump or turbine. What is that H sub P term represent from last time? There's any machinery that penetrate into my flow, like a pump or turbine, and it's represented by the work per unit mass, W sub S. S stands for shaft. Divided by gravity. All right, and it has, according to our convention of first law of the control volume, flow in and out, heat added, Q and work, Ws of kilojoule per kilogram. Have you seen this diagram before? For a control volume in thermodynamics, not in fluid mechanics. But have you? Right? So we are now assuming adiabatic process, and this Ws in your thermal for the first law in the control volume represent the work per unit mass in this control volume. And it's positive work done by the fluid. And as such, if I have a device that extract work from the fluid, like a turbine, an air turbine, a water turbine, hydraulic turbine, this term will be plus. If I have a pump, then this term will be negative, because pump represents energy added to the fluid. So all the sign convention now is all come to bear. And then in a lecture or two, I will show you exactly how this equation come about in detail, starting from this diagram to a formulation of energy equation specifically for pipe flow. So let me stop. This is all repeat from last lecture, but it's very important you understand the sign, all the nomenclature, etc., etc. I like to stand corrected myself. I don't want to use the P. The P stands for pump. So it's only applicable to this in-class example. In general, I will call this H sub S, stands for shaft work. So it can be plus or minus depending on whether the device is a pump or turbine. So this is very important as a starting point. Do you see it? Aside from the detailed derivation, dot, 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 it's my nomenclature of algebra and in-depth, deep-end derivation, which we will do. But starting from here, take my word, we have now an energy equation that somewhat, in some aspect, look like Bernoulli, but it's not. That's a very long repeat, and I haven't answered that homework problem yet. But do you see how the pieces fit together? Now, jumping ahead, before I finish the homework, jumping ahead, in order to relate the power given in this problem from that water pump, in your thermal, so how do I relate power to W sub S so that I can get kilowatt or horsepower related to the flow system? W sub S actually carry a special name in thermodynamics: energy per unit mass, work per unit mass. What is that called? Enthalpy per unit mass. Specific work. So this is in your thermal what is called specific work. So put on your thermodynamic hat, forget about fluid for the time being. And I'm sure you've done this type of problem by midterm now in thermal, which is nothing but first law, control law on pump, turbine. How do I go from specific work, which is in the units of kilojoule per kilogram, per unit mass to actual power in, say, kilowatts. You multiply by what? By m dot, very good. In fluid, how do I replace the m dot? Say it louder. Rho VA, very good. Rho VA. And that's what we will do. So thermal found in mid-fluid. Say hello to each other. All right, and that's what we will do. So this equation will be used repeatedly for many of your homework. That allows us to analyze, again, what I call full system. Not system is not piston and cylinder. Full system meaning set of plumbing, pipe, elbow, valve, pump, turbine in a power plant or in a petroleum refinery, etc., etc. Right? So that is the last piece that I run out of time last time to relate to the homework problem, sorry, for the in-class problem that we will be doing momentarily. But no, all these 10 minutes in span, I haven't answered the question yet, how to finish this problem. All the quantity here can be determined. Tell me about the velocity, that should be obvious. It's the same because the same diameter pipe. P are given, change in elevation is given. Any pump or turbine? No. Here's the final catch. What must H sub L be? And I keep changing nomenclature, I apologize for that. There I use H sub F, so I should use H sub F in here. Friction. But in your text, sometimes they use L, stands for loss. This stands for friction, so please, hopefully it doesn't confuse you. What can you tell me about H sub F? For that to make sense, what must be H sub F? Has to be greater than 0. If I plug in that number here on the left and the right, and this turns out to be positive, my assumption is correct. Turns out it was wrong. Turns out the flow actually go downhill. And the only way you get that answer is use energy equation. You do not know a priori. There's no way. Yes?
So, so you know the height, you know the density because you know that it's water. So, and you know the gravitational constant, and you know the difference in pressure.
Mm-hmm.
So couldn't you just say that like rho GH, whichever one is bigger, either rho GH or pressure, whichever one's greater, it's either going to be like independent of area.
No,
Why?
that's presumptuous. Because the only way I can tell whether the flow go up or downhill is the full use of the energy equation. You are just using pieces of it. You're just telling yourself, oh, I know the pressure change, I know the elevation change. But you haven't included the frictional loss. That's the difference. Okay? So it's very tricky. It's a good homework to tell you that you've got to look at the energy equation in total to answer that question. It seems very tempting to answer this question by intuition, but your intuition is wrong. The only way you can tell is energy, full energy equation. Okay? So what's different is now the energy equation has a new unconventional term called losses. Losses. That piece that you deal with in your second law of thermodynamics. And it has to be accounted for. You cannot destroy energy. So energy to overcome friction is accounted for right here. If you don't account for that piece, you cannot tell me which way the flow will go. Are you convinced now? Any question on the nomenclature of the energy equation? As we get more and more in depth, we have more nomenclature, and I will post a nomenclature sheet in the next lecture for you to read. But aside from that, here's the assignment. Chapter 5.3, control volume, energy equation. So we are taking a step back, and there will be assignment in chapter 5, exclusively dealing with the use of energy equation. Handout on energy equation, I haven't posted. haven't given to Mike yet, but it should be available end of today. It's a 2-page type derivation in detail of how we go from this first law, control volume, to the energy equation that I show you now, exclusively for fluid and mainly for pipe flow. So that we will go over maybe even next lecture, if not the lecture after. And in doing that, it's a little bit in depth. In doing that, you show how this X sub shaft come about, but more importantly, how this head losses is originated from. It has to do with entropy. Okay? Which you probably don't want to hear the word entropy, because it's just very confusing. But here's one example to help you to get a better feel for what entropy is. That friction, that losses, that irreversibility appear here as part of the energy. It's just energy that is gone in space, never come back. All right, so that will forthcoming. Homework is 2.5 hours. The one piece of that is the in-class, which I will explain in detail, has to do with Moody diagram, the laminar frictional head loss. The other two problems is very straightforward. I won't touch on it. I think first half of the semester, I try to touch on each and every homework. Second half, I try to kind of loosen that a little bit. I don't want to continue to spoon feed you. So you may have to do a little bit more soul searching on the homework, but if on problems that are very challenging, I will touch on it. But those are relatively straightforward. And same with the solution to the homework. The feedback said, sometimes we don't need to spend time on it, and I totally agree. So moving forward, unless you ask me, like today, I won't necessarily spend time on the homework. But it's up to you to read it in the poster solution. Okay, are we now ready to go on to solving this problem? Okay, so what we have, as repeating the problem statement last time, is that I have a flow system that consists of intake from a reservoir, a pump that adds energy to the fluid, the water, at a rate of 35 kilowatt, and the efficiency of the pump is 100%, low losses. Tell me the exit velocity for a diameter of a nozzle of 5 centimeters. And the change in elevation of the pump is 2 meters from the free surface of the water. It's a free jet,